introduce something that we can find with matrices. It's called a determinant. For a lot of people, it kind of sounds like that piece of the quadratic formula that's underneath the square root. That's called a discriminant. So sometimes people get those words jumbled up in terms of math vocabulary. But determinant is always related to a matrix. Okay, so just really quickly, a determinant is a real number associated with a square matrix. So there are some things that we can only do if the matrices are square, and one of those things is an inverse. Only square matrices have inverses, although not every square matrix has an inverse. And then now we have the determinant. Determinant is only found for square matrices. And the thing to remember about the determinant is a real number associated with that matrix. It is not another matrix. So in the warm-up that you guys just completed, you found the inverse matrix. Okay, so you were given a matrix and your answer looks like a matrix. When you calculate a determinant, you get something that might look like a matrix, but in the end your answer is just a single number. So kind of be aware of that. Here's some notes we'll take about notation and calculating the determinant. So we're going to work with the same matrix that we used for inverses. So matrix A, we're going to let it be first row AB, second row CD. And there are really two forms of notation that you can use for a determinant. One of them looks sort of like what we might think of absolute value. Instead of like matrix bars or brackets, it's just vertical lines around A. So when you see that in matrices, you know that that's asking you to find a determinant. Okay. And you're going to see on some of my slides, I'll even put those vertical bars where the matrix brackets are, and I'll have rows and columns. And anytime you just see that around a matrix, it means not really the matrix, but the determinant of the matrix. What is that real number? The other notation that you might see is just sort of an abbreviation, DETA. So that means the determinant of A. If you kind of think back to all that matrix work you're doing in your calculators, when we go to the math menu and we're trying to do row echelon form and reduce row echelon form, DET was the first thing in that menu. So you can do determinants in the calculator. And then this is how you calculate the determinant. Okay, so depending on which notation you use to calculate the determinant, okay, I'm going to show you where I rewrite this matrix. But notice I'm not using matrix brackets, I'm using just the straight vertical bar, so that's telling me calculate the determinant of the 2 by 2 matrix. And the determinant is AD minus BC. Seem familiar? Yes! It's that very first piece to the inverse, the thing that you were doing in the warm-up, right? So where we had a rule for the inverse in our notes last week, and we had like 1 over AD minus BC, sometimes when you look up the rule for the inverse of a 2 by 2 matrix, it might look like this. 1 over the determinant of it. And then times that. Okay. All right, excellent. So I've got some examples I want you to practice, and this should be not too terrible. Find the determinant of each matrix. So I'll kind of run through the first one, and then I'll give you a couple to do. So this time I'm going to switch up my notation. I'm going to use that vertical line bars around A. So that means the determinant of matrix A. And I would do AD, which is -1, minus, you're always subtracting the product of these diagonals, and then 2 times 3 is 6. So the determinant of A is equal to -7. Remember, the answer to the determinant is not a matrix. It's just a real number associated with that matrix. So if you would, go ahead and calculate the determinants for these two square matrices. And then as you're getting your answers, if you would just check with your table groups and see if you're getting the same thing. We'll see if we can calculate those determinants correctly. Okay, Tatum, what did you guys get for B? 10? And notice I switched up my notation there using the DET abbreviation. Anna, what did you guys get for our determinant of C? 0? Okay, are we in agreement with that among the group? I heard a good conversation over here. Maybe somebody forgot that we multiplying by 0 is 0, right? But those are the little things in determinants. Hey, those are the little things in determinants that come back to haunt us, and when we get to the 3 by 3, that 0 is even more of like a trickster. I don't know how it does it, but it always convinces us that it's non-zero. Okay, so you have to be really careful with that. By calculating those two determinants, we would know that this matrix here in C does not have an inverse, right? Because then it would be 1 over 0, which is undefined. So we can say immediately that it doesn't have an inverse. Okay, so that's a 2 by 2 determinant. We're going to talk about 3 by 3 determinants. They go in alphabetical order. That's a good thing. We have to include Okay, so we've got a 3 by 3 matrix. Matrix A is ABC in the first row, DEF in the second row, and GHI in the third row. And our job is to calculate the determinant. Now, not everyone can see Sierra because she's in the back of the room, but she was like, just like this. What about a big X, right? That would be awesome. But then she, I was like, oh, maybe not so much. And she's like, oh, what about DNF? Then you never get to DNF, right? So they have something to do with the determinant. So, basically what we need is like, we're going to go down on the diagonal. So we're going to get that AEI. But then we need all the other diagonals from the top left to the, down the right. And so the next one would be BF, but could you imagine if this were three-dimensional and you wrap around your matrix and it would be G? And then the third diagonal would be C and you would wrap around the matrix and it would come back to DH. But we're not going to mentally wrap around our matrix. An easy fix for this is copy the first two columns. And we're going to calculate a 3 by 3 determinant. Copy the first two columns. You could copy all three columns, but the diagonals are never going to reach the third column, so you don't need it. Okay, so you only need to copy the first two. And then we're going to do our diagonals going down from left to right. So we're going to have AEI We'll add to it BFG. And add to that CDH. So the sum of those diagonals is our first piece of the determinant. And then we're going to subtract from that all the diagonals going up from the bottom left to right. So I will multiply GEC plus HFA plus IDD. Now, of course, this will be a little bit easier when you're actually doing a real matrix because those will be numbers, and then you'll be able to add them together, right? So you'll have a number for this blue piece, and then you're going to subtract from it the number for the red piece. So I'm going to write this out. AEI plus BFG plus CDH. Add those all together, so I'm going to protect them with a group of parentheses, although it doesn't really matter here in terms of order of operations. And then subtract from that, and I'm going to put in another group of parentheses, GEC plus HFA plus IDD. Now, that set of parentheses is really important because you have to add those three diagonals together before you subtract the number. Now, again, this will be a little bit easier when they're actually numbers because then you can just add them together. Fair. However, you still need to know how it is done, right? Somebody programs your calculator, so someone has to know how to do it. That could be you someday. Who knows what the next greatest piece of technology is. Okay, so let's calculate the determinant for matrix A. Now, I'm going to do a little bit of just like notation work here and say I want to do the determinant of A. So I'm going to use my vertical bars. If you see the matrix, you don't have to necessarily rewrite that, but I'm going to do that because you might come to a problem where all you see are the 3 rows, 3 columns, and then the vertical bars. And those vertical bars would tell you to do the determinant. It's not giving you a matrix. It's calling for a determinant. So you need to know how to read that notation. And then I'm going to copy my first 2 columns. And I like to do my work much like I presented it on the other slide. I'm going to draw my diagonals. So 1 times -1 times 0 is 0. Plus -2 times 2 times 1, -4, plus -1 times 0 times -2, 0. And you can see where if there's a 0 in your 3 by 3, you got to be really careful. Anything times 0 is 0. And then I do the same thing going up. 1 times -1 times -1 is 1. Plus -2 times 2 times 1 is -4. Plus 0. This stuff that you do, like if you show me what your diagonals are multiplying out to be, that's going to be a lifesaver on your quiz and test in terms of showing your work and getting partial points, right? If I see that you accidentally did this -1 times 0 times -2 and you got 2, I just know that you forgot that multiplying by 0 is 0. And so I can take off for that tiny thing and keep grading your work as is. But if you don't show work, I can't always see that, right? Okay, so always remember that these at the bottom, the sum of the diagonals going down always have to be in front of the subtraction sign. So that's just going to be -4 minus, and then the sum, 1 plus -4 plus 0 would be -3, you're always subtracting, so that would be minus a -3, which is really plus 3, and so the -1 is your determinant. So yeah, I get it. The 3 by 3 is a lot of work in terms of like I could just type that into my calculator, but I mean it's not so terrible. You can imagine like if you were going to do a 4 by 4, then you'd have to repeat 3 columns. I'm not going to ask you to do higher without a calculator. But you could imagine, like, now you see why technology is so valuable, because as it gets larger and larger, and we're always focused on, let's learn it for the small, let's learn the process, let's learn how it works. It can be applied to the large, which makes more sense in the real world if we were working with a large set of data. Okay, so use calculators for determinants of square matrices larger than 3 by 3. Or if you came like on the homework, if you have a matrix with really big numbers or you have decimals, then yeah, plug that into your calculator. That's not really something I would say do by hand. Okay, so we're going to move on. We're going to talk about some uses for the matrix, the determinant of a matrix, because there are many uses. So I think we do 2 or 3 today, and then you have 2 tomorrow. So what can a matrix do? Or sorry, a determinant of a matrix do? If you're given 3 points to a triangle that exists on the coordinate plane, so points would come in xy ordered pairs, and we would have 3 different points. So I've labeled them x sub 1, y sub 1, x sub 2, y sub 2, x sub 3, y sub 3. You can calculate the area of the triangle using the determinant of a matrix. So that looks like, and I'm going to say area of the triangle instead of A equals, so I don't want it to be a matrix, but the area of the triangle equals plus or minus 1/2. And think about your normal equation of a triangle always has that like half of a rectangle or divide by 2 piece. Now the plus or minus will come in handy, like if your determinant is negative, it would make sense for area to be negative, so then you multiply by the -1/2 and the area becomes positive. If your determinant is positive, then you want to keep area positive, so you multiply by the positive 1/2. So you don't multiply by both plus or minus, you multiply by whichever one you need to get a positive answer. And then we're going to have the determinant. And we just, in each row, put a coordinate, but we need it to be square, so the last column is going to be 1. Now, there is a proof for this. If you're interested in looking at the proof, you could look online, or I'm not sure if it's in the textbook at the end of chapter 8. I'd have to double check. But we're not going to take the time to prove it. We're just going to say, okay, we accept it. But if you were interested, you could look at that. And so you're just going to do the determinant for that set of 3 by 3 matrix, multiply whatever your result is by plus or minus 1/2 to get you a positive number, and that's your area in square units. So we'll do an example. Wrong thing I pushed. Did everybody get that down? Let's find the area of a triangle whose vertices are at 0, 0, 4, 1, and 2, 5. Now, I am very well aware that you can find the area of this triangle different ways. You have a lot of information from geometry, okay? But this is just another method to find the area of a triangle. So I'm going to start off with area equals plus or minus 1/2. And right now I don't know what it's going to be, plus or negative. It'll depend on what my determinant comes out to be. My x sub 1, y sub 1, I'm going to call 0, 0. So my first row is 0, 0, 1. X sub 2, y sub 2, I'm going to use that second point for 1. And then the third column is always a 1. And then the third point, 2, 5. 2, 5, 1. So that's the setup. And now you need to run through the method to find the determinant. So I'll give you a little bit of time on your own, see if you can calculate. Right now, just ignore the plus or minus 1/2. Focus on the determinant. You can check with your members as you go. Are you getting the same numbers for diagonal? What about when you add the diagonal? And maybe see how easy it is to make a small mistake.
Is the plus or minus on the 1/2 to know, like, if your answer, like, if your determinant is negative or negative?
Yeah.
It's not on your determinant.
No.
Make sure
Only one answer makes sense in geometry for area, or in space for area, positive. Yep. So as I'm walking around, people are doing a great job here. Your determinant comes out to be 18. So your area is plus or minus 1/2 times your determinant 18. And then this is, again, choose the one that keeps the positive area. So since your determinant is positive, multiply by positive 1/2. So the answer should be 9. And I told a few groups who were finished as I was walking around, in context of area, that should always come with a label. So we would say 9 square units. Okay, not so bad, right? Well, it doesn't get too much more terrible. Okay, can I go to the next? Okay, the other thing that we can do is test for collinear points. What does it mean to be collinear? Here are some geometry uses. On the same line. Now, remember we just did the area of a triangle, right? And so think about for the area of the triangle, if you have 3 points in space, then you have some space inside them, right? And what happens as those 3 points in space get closer and closer to being collinear? What's happening to my area as I'm like shrinking that one point in? What's that? Yeah, they're getting closer and closer to being collinear. What's happening to the area? It's getting smaller and smaller. In fact, what would be the area of a triangle, in quotes, if all 3 vertices were on the same line? 0. It wouldn't really be a triangle, right? Okay, but could you imagine just like collapsing until it was on there? And then there's no area, there is no triangle. So to test, you don't really need that plus or minus 1/2 for this, because plus or minus 1/2 times 0 is going to be 0, right? But the test for whether or not 3 points are collinear is if the determinant of the 3 points is equal to 0. So this says the points x sub 1, y sub 1, x sub 2, y sub 2, x sub 3, y sub 3 are collinear if and only if the determinant is equal to 0. So if you're ever asked, are these 3 points collinear? Calculate the determinant there. If it's equal to 0, yes, they are collinear. If it's not equal to 0, no, they're not collinear. Those would be your 2 answers. If you answer no, technically you could find the area of the triangle formed by the 2 or by the 3 points by multiplying by plus or minus 1/2. Okay? Okay, so let's just do a quick example in our test for collinear points. And then you'll end with a little bit of time to work. Oh, nice. Are the points -2, 4, 3, 1, and 6, -4 collinear? Well, how will we tell? Is their determinant equal to 0? So I'll give you a little bit of time to calculate. Okay, so as I'm walking around, we're coming up with -16 for our determinant. Are these points collinear? No. No. So make sure that you answer the question. If it's not just calculate the determinant, you have to make a statement. Are they collinear? Yes. Are they collinear? No. Okay. Your homework assignment is in the textbook. If you did not work on your quiz corrections yesterday, you could also work on those and turn them in to me today. I'll accept them. If you didn't have anything highlighted, that means you have no corrections and you can turn it in right away. You'll have a 100%.